Have you ever stopped to think about how you can stream a video from a server on the other side of the planet just as easily as you can pull up a file on your local network? Well, the secret to that magic is an unsung hero of the internet, the Border Gateway Protocol, or BGP. So let's dive into the protocol that literally glues our entire digital world together. You know, this image really hits on a core idea that most people miss. The internet isn't one giant monolithic cloud. It's actually a massive, sprawling patchwork of thousands of separate, independent networks, all with their own rules and priorities. So, what stops this whole thing from descending into absolute chaos? Well, that's BGP. It's the elegant, essential stitching that holds all these disparate pieces together, making them act like one single global internet. So, how in the world does BGP work its magic? Well, it all starts with understanding the internet's most fundamental building block. Let's peel back the layers and look at the core unit that makes up the entire structure of the internet. And here it is, the autonomous system, or AS for short. The easiest way to think of an AS is just as a big network with a single unified routing policy. We're talking about your internet service provider, a big university, or a tech giant like Google or Amazon. Each one of these gets its own unique ID, called an autonomous system number, or ASN. Now here's the crucial part. BGP's job is to figure out the best path between these huge systems, and it does that based on policy, things like business agreements and cost, not just on raw speed, which is what most internal network protocols care about. Okay, so we've got these huge autonomous systems. How do they actually talk to each other and decide where to send traffic? Well, BGP provides the language for this global conversation, and it's a very precise, very orderly process that keeps the entire internet in sync. BGP basically has two main flavors. As you can see here, you have eBGP, which stands for external BGP. That's the language routers use to talk between different autonomous systems. Then you have iBGP, or internal BGP, which is used to share all that external information within your own network. It's incredibly flexible, and all this communication happens over a reliable connection on TCP port 179, which means BGP gets to focus purely on routing decisions without ever having to worry about lost messages. Now, before any routes can be exchanged, two BGP routers have to perform a very specific, very formal handshake. This whole process is dictated by what's called a finite state machine, which you're looking at right here. It's a super strict sequence. A router starts in an idle state. It tries to connect. It sends an open message to basically say, "Hi, I'm this router, and here's what I can do." It then waits for a confirmation, and only when both sides have agreed does it finally move to the established state. This whole rigid dance is about building trust and making sure both routers are ready to exchange information reliably. And believe it or not, that entire complex conversation is built on just 4 simple message types. The open message, like we just saw, is the initial hello. Keep alive messages are like a constant little heartbeat, just a, "Hey, you still there?" every 60 seconds or so. The update message is the real workhorse. This is where new routes are advertised and old, dead-end paths are withdrawn. And finally, if anything goes wrong, a notification message is sent to immediately tear down the connection. It's simple, but incredibly effective. All right, so routers are connected, they're talking. But what happens when a router learns about multiple ways to get to the same destination? It can't use them all. It has to pick just one. This is where we get to the real intelligence of BGP, its powerful decision-making process. Think of this whole thing like a route processing assembly line. A neighbor router sends a bunch of possible routes, and they all land in a local inbox called the RIB in. Then, the BGP decision process, the brain of the operation, runs its algorithm to pick the single best path for every destination. Only that one winning path gets installed in the router's main forwarding table, and after passing through some policy filters, gets advertised from the RIB out to all the other neighbors. So, how does BGP even decide what's best? It's not just about speed. Instead, it looks at a rich set of information attached to each route, called path attributes. You can think of these like a resume for a route. And the most critical attribute of all is the AS path. It's literally a list of every single autonomous system a route has traveled through. This gives BGP a brilliantly simple, built-in way to prevent loops. If a router ever sees its own AS number in the path of an incoming route, it knows that route is a loop, and it drops it instantly. Beyond those basic metrics, other attributes act as powerful tuning knobs for network engineers. Local pref, or local preference, is used inside your own network to tell all your routers which exit point is the best one to use. MED, the multi-exit discriminator, is basically a suggestion you make to your neighbors about which of your entry points they should prefer. And then you have communities, which are like special tags you can attach to routes to signal for specific handling. These are the tools that turn BGP from just a routing protocol into a full-blown traffic engineering toolkit. This funnel visualizes the decision engine perfectly. BGP takes all the possible paths for a single destination and runs them through this strict, deterministic, multi-step tie-breaking process. It's like a tournament. It checks the first criterion. Is there a winner? If not, if there's a tie, it moves to the next criterion, like local preference. Still a tie? It moves to the next, like which one has the shortest AS path. And it keeps going down this list until one and only one path is left standing. There's no ambiguity. One path wins, and that's the one that gets installed. Okay, let's look at a really simple scenario to see this in action. Your network needs to reach some destination. It learns about two possible paths. Path A goes through 3 other autonomous systems to get there. Path B only goes through 2. Assuming all the earlier tiebreakers were equal, BGP gets to the AS path length step. It sees that Path B is shorter, only 2 AS hops versus 3, so Path B wins. It's that simple, and it's always deterministic. BGP installs Path B as the best route and starts sending traffic that way. But here's the thing. BGP was designed over 30 years ago, back in a much more trusting, academic era of the internet. And that original design, which was basically built on a digital handshake and implied trust, left it with some pretty significant security holes. So what are we doing today to patch them up? This slide shows the classic BGP hijack, and it's scarily simple. An attacker's network can just start announcing to the world that it owns the IP addresses of, say, a major bank. The fundamental problem is that BGP was built to verify connectivity, can I reach this network, not identity, are you who you say you are. So other networks on the internet might just believe this fake announcement and start sending all of that bank's traffic, maybe your traffic, straight to the attacker. So how do we fix this giant hole? Well, the modern solution is something called RPKI, which stands for Resource Public Key Infrastructure. The best way to think of it is as a digital certificate of authenticity for internet routes. It lets an organization create a cryptographically signed record that proves they are the legitimate owner of their IP address space. So now, when a route comes in, a router can check it against this global database. If it's valid, great, the route is accepted. If it's invalid, it gets dropped immediately. This makes hijacking much, much harder to pull off. You know, BGP has evolved way beyond just connecting internet service providers together. Today, it's become a critical tool for building the modern cloud, for delivering content at lightning speed, and even for defending against massive cyber attacks. This slide really shows just how versatile BGP is today. Of course, it's still the backbone for ISPs, but it's also how big companies build private, direct connections to the cloud. It's the magic behind Anycast, where services like DNS can be announced from dozens of places at once, and you automatically get connected to the one closest to you. And, critically, it's a key weapon in fighting DDoS attacks, by letting us redirect all that malicious traffic to specialized scrubbing centers before it ever hits its target. But as networks get bigger and the internet itself grows, we're talking over 1 million routes in the global table now, new challenges pop up. Inside a large network, having every single router talk directly to every other router, what we call a full mesh, becomes unmanageable chaos. It's like having 100 people in a room all trying to yell at each other at once. The solution is a clever design called route reflectors. You designate 1 or 2 routers to act as a central hub or a town crier. They learn all the routes, and then they reflect them out to everyone else. This hub-and-spoke model brings order to the chaos and allows IBGP to scale to incredible sizes. So let's wrap this up with the key takeaways. First, BGP is absolutely essential. It's the only protocol on the planet that can handle the internet's mind-boggling scale. Second, it's policy-driven, always prioritizing business rules and engineering choices over just raw speed. Third, it is definitely complex and requires a lot of careful planning to manage correctly. And finally, and maybe most importantly, it is constantly evolving. Security features like RPKI are no longer just nice-to-haves, they are becoming a modern necessity. And that really brings us to the final, thought-provoking question for this explainer. BGP was born in an era of mutual trust between a small community of network operators. But today, we're moving rapidly into a future defined by zero-trust security models. So how does this foundational 30-year-old protocol continue to adapt and secure the internet of tomorrow? Well, that is the fascinating challenge that network engineers are tackling every single day, working to secure the very fabric of our connected world.